Hey, hi there. So welcome to this session on bootstrapping UVM-based verification with UART Testbench Part 2. So as a part of our series Part 1, we have established the UART DUT from its interface point of view and from its software view point of view, and we looked at the bunch of tests that are supported in the UART Testbench, and we picked one of the test that's a word format poll test. We picked that test and we looked at that test was able to transmit 2 characters and receive 2 characters, and it used the mechanism of polling to establish the process of transmission and reception, and then we correlated the logs to waves to confirm that it was doing that indeed. As a part of this session, which is a part 2, what we will do is we'll take that particular test. So far we have not looked at the test code, right? Like how exactly the test code has been written, and then we have not looked at like which are the sequences that are invoked, environment. We have not looked at any code at all, right? So in this part of this session we will look at the code as to how that particular scenario has been created. So as we talked about, we have covered this as a part of part 1. We looked at the interface view of the DUT. We had a APB interface, and the APB interface was used to access both the data and the control path. We had the TXT and RXT pins where the serialized data was sent out, and the APB interface was used to configure the UART, right, in terms of like what's the format that we need to transmit, in terms of like there's a 5-bit, 6-bit, 7-bit, 8 bits, whether the parity is enabled, how many stops bits do we need to transmit, and then various interrupt characteristics. All of those we configured it using the control registers, and then by writing and reading the data register, we were able to program the UART with the data that needs to be transmitted, right? And then that formed the software view of DUT for us. Then we have looked at scenarios to test, we have looked at simulation log, we have looked at the waveforms. Just try to make sure that you have that on the top of your head. Like for example, the series of polling that happened on LSR registers, right? So all those patterns, right? The 2 writes to the TXT registers, 2 reads to the RXT registers, and on the serial line we saw how the data was transmitted starting from LSB, and how that overall read and write registers was all available in the log file. So we have looked at all those, right? So now what we want to understand is how did a UVM test bench accomplished those things, right? That's what we are going to be focusing as a part of this session. This is what will be our agenda. We'll look at the directory structure, then we'll go through the test bench for UART. We'll start with the top. The UVM top of anything is the test that we are running, then how the test instances environment instances agents, and then test configures the environment, which in turn configures the agent, and then test invokes the sequences which lead to stimulus generation, and then the stimulus gets executed on the DUT with the help of the environment that is available, and then the scoreboards capture through monitors what is happening on the interface, and then do the checks, and then coverage covers it, right? So we will look at each of these components, how they are implemented in the UVM. A very quick refresher about the core concepts. So we are going to look at that the test intent and environment. Primarily this concept is that the tests, whatever the test wants to do, what is it the test wants to do? It wants to configure the environment for a particular configuration and then generate the scenario that is appropriate for that particular configuration, right? That's what exactly what the test wants to do. It doesn't want to do the self-checking. For example, as much as possible, test wants to just focus on configuring the design, then stimulating the design, and the rest everything it expects environment to take care. Okay, that is the expectation. So the test intent is that it will generate the stimulus and then environment will execute. If you remember, we have kind of correlated this to an instruction and a processor. So in this case, test will be generating various sequence items and the environment will be processing them, right? So whether that's really happening or not, we will see it in this example. Make sure you pay attention to those components versus objects. We have already talked about components are throughout the simulation. They exist and they have a thread to process objects. They get created, multiple of them get created. The primary object for us is the starting with sequence, and then sequence generating the series of sequence items. We look at that. Then configuration database. The configuration database being able to pass the configuration information hierarchically through the UVM Testbench, starting from the test to environment to agents, and then the components present within the agent, which are your driver, monitor and sequencer, right? How do we pass the information? We look at those examples. Phases, we have identified 3 primary phases. We have build phase, we have run phase, and we have cleanup phase. Of course, within each of those we have multiple phases. We are going to be primarily looking at, our interest is going to be build, connect, run, and then report and check, right? So there are multiple of them, but we are going to focus on these phases. They are the main key phases. Okay, and then we look at the factory. Of course, we are not doing any factory override in this particular test bench, as it doesn't require that capabilities at this point of time, but at least factory involves 3 steps: registration, then creation, override, right? But we will still be looking at registration and creation. Override, we will not be looking at it, but we'll look at it when we do the deep dive session. Then modeling transactions. How do we really create sequence items? We will briefly look at it over here, but eventually after this session, the bootstrapping will continue with the APB master agent. So in the APB master agent, when we talk about it, you will be looking at modeling transaction in a much more detail. Okay, so in that session, we are going to be covering the agent, right? So we will not be covering in detail agent part in this particular session. So in this session, essentially what we are thinking is that we have understood, right? The primary business case for the UVM is that somebody is selling and we are taking it and putting it together and building testbench. So we will think like that and do it, right? So we think that all the agents are available to us. We integrate those agents, we build coverage, we build scoreboard, we build sequences, we build tests and do the verification, right? But as a separate session wherein how to build the agent itself, right? So that we'll do it as a separate session, so that way it gives both the sides of perspective, as a user of verification components as well as a developer of those core verification components. So you'll get to see both the sides. So when you do the APB agent session, you will be able to see how to build a UVM agent. And in this session, we are going to assume that that particular agent is provided to us and we will just focus on using it. That way 2 things happen. One is we get that user versus the developer perspective from the agent point of view, and second, also it allows us to focus on the like the core verification objective and divides the problem. Otherwise, if you put everything together, it becomes very hard to absorb. So modeling transactions we will be seeing briefly over here, but we will look at it much more in depth when you do the master the APB agent after this particular session. And then end of test, we have been talking about it, like raise objection, drop objection. What does exactly, how exactly does that happen? We'll look at it, right? We are not going to go into whys. We are going to be focusing on how to do some things, right? So that we are able to get to a state like a ready every day. That's our focus, right? So we want you to be ready to do something UVM immediately after this session. Then TLM for communication, we are going to look at how to use TLMs, right? So we're not going to go very deep into TLM. That we will do in the deep dive sessions, but here we are going to use the TLMs and connect our components and assume that the transactions will flow through them, right? How exactly, the more details and more depth we'll do in the deep dive. And then we look at the sequencers, because we are going to be using the agent, so they will have sequence and sequencers. Our primary interest is going to be how to create sequences, how to start them. That is the angle that we are going to focus on. Internally, how does the agent function? That part we are not going to worry too much about it. Just briefly, we are going to touch base. That part we will cover when you go to the APB agent construction, as I talked about. And then we look at few shortcut macros. So this is the overall. What we are going to do is we are going to see, this is this is all going to now fit in very beautifully. So we have looked at the UART specification from both the interface point of view as well as the software point of view. We have briefly understood about UVM, what is a base class hierarchy, what each one of them do. We have had a brief introduction to all the core concepts. Now in this session we will put all of them together: core concepts, then the your base classes, and then with respect to UART, how are we going to apply, right? So we will stitch all of it together to present you a clean, coherent picture as to how do you build test benches in UVM. So when we learn something new, repetition is a part of it. Unless we repeat it few times, the key concepts are not going to sink in, right? So base class hierarchy is one such key concept. So we are going to repetitively look at this again and again so that it sort of sinks in. So think about it like this: whatever repeats in these sessions, repetition is a sign that it is important. Okay, so our object hierarchy, this we have seen it. So we have UVM object at its core, and then we have two hierarchies. We have a transaction hierarchy, we have a transactor hierarchy. We can also call this as an object hierarchy as well as a component hierarchy. Both of these two terms are being used. The latter one is more popular. So we are going to construct most of our objects in the form of sequence items, and then the sequence is going to lead to generation of different sequence items, and sequence items are processed by agent to apply it to the DUT or observe the DUT interface and create the transactions from the monitor. And then we have the component hierarchy. The component hierarchy is the one that stays throughout the simulation. UVM component is the main base class, in that the main functionality provided by UVM component, the hierarchical state that it sets up, and second thing that it provides is the phasing, right? So phasing is the main value addition that is provided by the UVM component base class. And then based on UVM component base class, you have a bunch of these other classes. Even your UVM test is based on your UVM component base class. What it means is, since they extend this particular class, they inherit all those virtual phasing methods which we need to implement: the build, connect, run, report, check. All those virtual functions will come in to part of UVM test, part of UVM driver, part of UVM environment. Each of these components that we are seeing inheriting over here will have those methods. And keep this point in mind that just because they have inherited, they don't need to populate all the virtual functions. Like we have been correlating these base classes to application forms. So many times what happens, in various application forms, something is not applicable to us, so we don't have to fill that detail, correct? Same thing, the same analogy carries over here. Although various fields are provided, various functions are provided, every component focuses on implementing what is relevant to that particular component, right? The rest of them it can ignore. For example, there may not be any activity left to do run phase in environment, because environment, once it has built it and constructed it, the run activity, right, we have already seen the run phase automatically gets launched for the rest of the components. In our FIFO test bench, for example, environment was launching the run tasks of all the components, but in the UVM, the core itself takes care of launching the run phase parallelly, right? So and then the individual component will do their job. So what does the environment do? It does nothing in the run phase, so it doesn't really need to populate the run phase, for example, right? So this way, although all the phases are available to all the components, every component will implement whatever it needs. That's all, right? Whatever it needs to perform the job for that particular test case, it will do. The third category is your various utility type of classes. We will have the RAL, you have the configuration databases, bunch of reporting things. We will see each one of them as to how exactly that gets implemented. Just keep this in mind. It's going to be how type of a session, and some things you may not fully understand the the depth of it. Don't worry about it. Take these concepts on face value, accept it, think about it commonsensically and absorb it. And you may have some questions, keep those in mind, make a note of it. When we do the deep dive, I am guaranteeing you that those all will get resolved. This is another piece of information that we will be repeatedly seeing. So we are going to be, the reason why we are seeing this picture is that to refresh and to make sure that we look at the examples for each one of these base classes. So like UVM test, then how do we create a UVM environment, and then the test passes the overall environment config, and then that environment config will contain the configuration for various agents, and then the individual agent configurations from the environment flow to their corresponding agents, and then that's how the environment gets constructed structurally, and then gets configured functionally to the requirement of the test. And once that particular configuration has been done, the test will pick up the sequences from the sequence library, and it's going to run on the corresponding sequencers. And then when it runs on the corresponding sequencers, the sequence item will get produced. Those will get communicated. For example, whatever runs on the sequencer will go to driver. Driver will drive it out on the DUT. The responses will show up. The monitor will monitor it and send it via this diamond is the analysis ports. It will send it to the different set of analysis components. The analysis components are nothing but our scoreboards, coverage monitors. So each one of them will take it, and the scoreboard will do the checking across interfaces whether the integrity is maintained or not. And then the coverage will do the coverage collection. So what we are going to do is we are going to look at one sample of each one of these. So the full test bench, each component we are going to demonstrate something, right? And as I talked about, we will not probably be looking at an overall agent. The agent itself we are going to look at it separately, because it's also called as UVC, right? So a universal verification component. So we will look at that separately because it deserves that attention. So first thing, we will start off with the directory structure. As we had talked about it, that the directory structure is also an important part of building the reusable test benches. So this is the directory structure. You will be able to, like when you get this UART example and when you untar it, you will be able to see this all the directories. So you have an UART example, you have agents. So in the agent directory, you have these 3 reusable agents that can be reused across projects. You have an APB agent, modem agent, and a UART agent. The APB agent is something that we are going to be doing deep dive after this session. For this session, we are assuming that these agents are available. We will not be looking at it, but we will be looking at it from the point of view of how to use them. Okay, and then the docs folder contains documentation about this UART 16550, various registers, interface pins that we had seen during the session 1. You can find more details about it in the docs folder. And then we have this protocol monitor folder, which contains an APB protocol monitor. Now you might be feeling slightly confused that you have heard this term monitor in the context of agent. Then you might be thinking, why is this monitor present here? Why is it not a part of the agent? So typically what happens is they are present at both the places. Okay, the monitor present within the agent just captures the transactions and sends it out to analysis components, but it generally doesn't worry about, sometimes, right, it depends on how you do it, it may not be doing the protocol checks. Okay, the reason why it might not be doing protocol checks is because many times checks are implemented using the SystemVerilog assertions and mainly the concurrent assertions, which are capable of capturing the temporal expressions, and those we cannot put it in the class, right? We have to put that in a separate either interface, module, or a program block, right? So that is a reason the APB protocol monitor, which doesn't monitor the lines and create a transaction. The APB protocol monitor these interface signals, and it validates the timing or the protocol that is taking place on the signals, right? So that is created separately in this protocol monitor. This also will be covered as the part of that agent session that we are going to be doing. And then in the RTL, you have the UART RTL present over here. We have the sim folder. In the sim folder, there is a simulation makefile. The makefile will contain targets to compile various of these components. You can compile test bench separately. You can compile the design separately, and you can run the simulation of individual tests, or you can run the regression by running all of the tests together. So you'll have all those targets present in this particular makefile. And then you have the UVM TB folder, and this is the folder that we are mainly interested in as a part of this session. So you have environment, in which we will have the UART env.sv, and then we'll have the bunch of high level test bench components like your scoreboards, checkers, coverage monitors. All those will be part of this env folder. And then we have the register model, which implements the RAL for the UART, whatever the register space that we have seen as a part of first session in the bootstrapping, all of those will be modeled in the RAL. So we will look at it. Then sequences. So we have these are the sequential sequences that individually run on an interface. Either you want to do the configuration or you want to transmit a character, receive a character. For all of them, there are independent sequences that run on a single sequencer. So we are going to be looking at those. And then we have a TB folder, which is your TB top, contains the module where DUT is instanced and connected to the SystemVerilog interfaces. The corresponding SystemVerilog interfaces, by the way, will be in the agent folder. For example, the APB interface will be in the APB agent folder. So in the TB folder, it will contain a TB top, which will be a module where we'll be instancing the UART DUT that's present in this particular folder, and then we will be connecting with the interfaces that are present in this agent, and then we'll be putting it in the config DB. So that part we will be seeing in the TB folder. Then you have bunch of tests, all the tests that we had shown for your register access, normal operation, error injection, all the tests that we had discussed as a part of session 1. All the test files, the UVM test files, are present in this test folder. And then we have the last one, virtual sequences. So virtual sequences are either set of sequences that can run on multiple sequencers, either sequentially or they can run parallelly. Okay, so at this point that concept might sound little confusing, but trust me, it will become clear partly when you look at this example, and second, it will become clear when we go do a deep dive on like this. We have a session on doing sequencer driver, right? So when we do that, it will definitely become very completely clear. So this is the overall directory structure, and my recommendation is that what you should be doing is you should always be using the Linux commands to get comfortable with the code. You can of course browse in the Windows, but you should try to use the Linux commands. Like for example, if I need to know what are all the files present in these folders, you should be able to use this command that I have called out. Maybe you want to make a note of it. The reason why I am showing you these two commands is with these two commands you will be able to explore any given test bench to you. This is a very important part, that if anybody gives you a test bench and asks you, okay, how many classes are present in this particular test bench, right? How will you find it out, right? And these two commands, if you remember, you can dissect and open any test bench and understand it. That is the that is how important these two commands are. So the first command gives you all the files, you can try it out and look at it, and second command combines this xargs, passes the files that are found by this find as an argument to grep. So all the files that are found by find, now the grep goes inside each one of those files and searches for this string. So when I say class dot star semicolon, it will list all the classes definition that is present in each of these files, right? So then I will come to know. Now with this I can keep adding more pipe and then find out more and more information, right? For example, I can pipe it and say give me all the classes that are UVM component, or give me all the classes that are UVM underscore sequence. And once the pattern of UVM test bench is set in your mind, as I have been repeatedly telling, if somebody asks you to write a test, what you are going to do? First look at the test. So how do I look at tests? So I'm going to use this command and then say xargs grep class, and I'm going to say one more pipe and say grep UVM test, right? So and it is going to list me all the tests. I'm going to open those tests and look for a sequence. If I want to know where a particular sequence is present, I'm going to run the same command and then again do xargs grep that particular sequence name, and then it will show me where that particular sequence is present. So this way, if you master these two commands, then you will be able to navigate, dissect, open any test bench and understand what is present in it. So make sure you try it out and get the clarity. Hey, let's look at the UART test bench. We are looking at the core view. We are not showing everything that is present. We are showing the details that are key, and the details that we would be really looking much deeper. So I think the main thing that we are not showing over here is the modem interface part, right? Rest everything I think we are able to show. So we have UART DUT and we have the APB bus. we have TXD, RXD, because what we are primarily interested in is being able to transmit something and receive something concurrently. That's the main scenario that we want to look at. So I'm showing those details, and as we have talked about, for every interface there is going to be a agent. Okay, so we have a APB agent that we will hook it up to the APB bus. We have driver, monitor, and we have a sequencer. So monitor is also going to be monitoring this APB bus and creating the APB sequence items. And then the same UART agent, we are instancing it as TX agent and RX agent. RX agent is going to be an active, that is why it is going to have driver and sequencer, whereas the TX agent is going to be a passive because it's only going to monitor it. Okay, so since it only monitors it, the sequencer and the driver are absent, but it's the instance of same agent configured as passive. And if you look at it, the monitor present in the agent is connecting to these two analysis components, right? So what are the analysis component we have? We have a transmit scoreboard and we have the receive scoreboard. So what they are going to do is, whenever we have done the transmission, whatever we write to TXD register, it's going to go into transmit scoreboard, and it will wait for that particular character to appear serially and then collected by this monitor and reported, and then it will do one-on-one comparison in the first in first out type of an order. Same thing on the receive scoreboard. So whatever we have started transmitting on the serial lines, once it has been transmitted, this monitor will give you the whatever the UART sequence item containing the data, and then we keep polling, let's say polling or interrupt, we extract that particular received item through the APB, and then the APB monitor is going to provide that transaction, and the receive scoreboard will do the check between those two. Okay, and then here if you look at it, the transmit scoreboard, whenever it has found a complete transaction, because we know that we should be doing the transmit coverage. Let's say if I want to, as we have talked about multiple times, if I want to cover LCR register, which configures the UART in terms of like how the formatting is done, right? So let's say we are like saying how many bits per character that we are transmitting, stop bit, parity bit, all those things, right? So I want to cover that. I should be covering it only when actual transmission has happened. Okay, so that's way what we are doing is, the scoreboard would know, right? So only when the actual transmission that has happened, which it has received from the APB monitor. We could have connected APB monitor also to the TXCow model, but then the scoreboard validates that and sends the similar type of an event to TXCow model, and then TXCow model samples the LCR register, because only when something has been transmitted, only at that point of time it will want to transmit LCR, because that is getting utilized. Okay, so that is why this is connected to scoreboard. But the primary reason, it could be connected directly to the monitors as well, but the primary thing you need to take care is, you need to sample when whatever you are sampling, like if you are sampling a register, whatever that you are sampling must be utilized by the DUT. Only after it is confirmed to be utilized by DUT, you can sample either directly from these monitors, or when it is validated from these other test bench components to indicate that it has really been used, then you sample the coverage. Otherwise, if you just sample when the register was written, it could become a false coverage. As we have talked about, if I sample the LCR register and then don't transmit or receive anything, then what is the use, right? So it's just a false coverage. It means something, but it means very little. That it just means register was programmed, but ultimately whatever we program has to be utilized. Then only we really test the logic. And then we have the RAL model, and the RAL model we will be looking at it. So it will model all the registers that are present in the UART DUT, and once it is modeled, what we do is, it has a concept called adapter. So you can do a very high level accesses to registers, saying with like RAL model.lcr.read or RAL model.lcr.write. At a very high level you do it, and then the RAL model will translate those accesses to the actual bus level transactions. Okay, what that means, we look at it, why do we need to abstract that, and what benefits does it provide, you will be seeing in this session as we go further. And then so this is the overall now view of the environment. We have not talked about environment, config and virtual sequencer, so let's talk about it. So let's start off with the virtual sequencer. So we have sequencers in the agent which handle one interface. Okay, so APB agent has a sequencer which handles the APB interface, and then the RxD, for example, is handled by the RxD interface is handled by the sequencer that is present in the UART Rx agent. Now this sequencer which is present in UART Rx agent cannot do anything like it cannot generate sequence items for a APB interface, for example, because this is connected to this driver. I'm not showing it to over here, but this sequencer is connected to this driver and this sequencer is connected to this driver, right? So they can only drive the interface signals on the corresponding interface they are connected. But what if I need to create a scenario wherein I want to launch something on both of them, right? So you have two options. One is you can directly do it in the test itself. It is possible to do it, but then what you do in one test may not become directly reusable in another test. So what UVM provides is it provides a concept of virtual sequencer. A virtual sequencer will not have any of its own interfaces, but a virtual sequencer will be sort of an intermediary. It will hold the handle for all the sequencers that are present in the test bench, and so you can now run a virtual sequence on virtual sequencer, and then depending on the type of the sequence, if it is a APB sequence, it will run it on a APB sequencer, and if it is a UART Rx type of a sequence, it will run it on the UART Rx sequencer. So it will orchestrate any sequence that you are starting across all the sequencers, right? So the test doesn't have to worry, and then that virtual sequence itself becomes reusable across different tests. So that is the idea of virtual sequencers, and typically all our tests will be launching the virtual sequences. So we will look at it how exactly it works. And then we have the environment config which contains the config for the different agents. Those configurations contain both structural as well as functional configuration information, as well as it will also contain the interfaces that are required for the agents to functions which we have connected at the TB top. So we will look at this. Okay, so how does this environment config works? And then in our UVM picture, if you remember, the environment box was part of the test, which is still true. I have just shown it in slightly different way. I've shown it slightly different way for two reasons. One is to save some space, and second, which is what is the real reason, is to show the fact that the test intent and environment are separate. Okay, to make that logical point also. Otherwise I could have somehow accommodated it, but mainly I wanted to show that distinction. So a test is primarily interacting with the environment using the environment config, through which it is configuring the environment both structurally and functionally, and then launching bunch of sequences on a virtual sequencer, and virtual sequencer coordinating sequences parallelly or sequentially running on different sequencers present in the environment, leading to the scenario we want. Okay, that's the overall big picture. So you have the test, it will configure the config, and after configuring the config, it will take bunch of virtual sequences and will launch it on the virtual sequencer. Those are the only two steps that it is going to do. Okay, so how it does it and how whole thing works, I think that is something that we will, for each one of these, so we will be looking at, for example, we'll be looking at the transmit scoreboard, we're looking at the TX coverage model, we look at the RAL, look at the environment config, receive scoreboard, I will leave it to you, you can find it out on the same line. We'll be looking at the virtual sequencer, we'll be looking at bunch of sequences and virtual sequences both as to how it runs, and we are not looking at any of the agents, but after this session we'll be doing deep dive in the APB agent, so you can look at that session. Rest of the UART agents, that is something for you to explore. Modem interface, if you are interested, you can, it's left to you to explore, but we will show you one flavor of all the types of components and we'll do deep dive. Rest of them will be same, you just have to understand the protocol details. So once you understand the UART protocol, you can understand the UART agent as well. It's not a big deal, but once you understand the concept of agent, how the driver is built, how the monitor is built, how the sequencers are built, the same concept applies everywhere. The difference is going to be the protocol that you are going to be implementing. We looked at directory structure, how the code is organized. This is another view. Here we are looking at how the code is organized in terms of SystemVerilog packages. Every major test bench component is put in a SystemVerilog package, and the benefits, as we know, it becomes, first of all, it separates the namespaces, and second, we can easily reuse in some other environment. So the way it's organized is you have a top level test package. Even this organization is hierarchical in nature. You have a top level test package, and then for each of the major test bench components like RAL is all put in this reg package, and we are importing everything. And then UART agent, right? If you remember, we had these three agents, right? So UART agent, APB agent, and modem agent, each one of them is a package which is imported. And then we have an environment package where all the environment as well as the analysis components that we are instancing in the environment are all put together. Then we have a virtual sequence package where all the parallelly or sequentially running virtual sequences which basically run on coordinated run on multiple sequencers within the environment, they have been put together. Then host interface sequence package is the set of sequences that run independently on individual sequencers. So it's actually the these virtual sequences are built using the host interface sequences. Okay, that's how they are built, because you combine essentially multiple individual sequencer running sequences into a virtual sequencer, because you're trying to coordinate them either by running parallel or running few of them sequentially and running next set of them parallel. You're coordinating the stimulus across multiple sequencers using the virtual sequence, and then in the individual sequence you are just focusing on one particular interface, right? So that's, they are all packaged separately and imported within this UART test package. So by doing this, what happens is, if I just want to reuse agent, then I don't need to worry about which all files I need to include in the environment, right? I just import that, and when you do that, what happens is, within, like I'm just showing within the APB package what happens, right? So all the files related to the APB are all included over here, right? So and then so that way when I import it, all these inclusions become part of the test package as well, so I don't have to now individually include these files and their contents. Okay, so similarly after that we have including all the tests. Okay, so that is the overall packaging for the test bench. So starting from the top to the individual agents, then you have the RAL, then you have the environment package, and then you have the virtual sequence package, and then the simple sequential sequences package. And inside each of these packages we again include their components. Like for example, the environment package, if you look at it, it also includes the agent packages, but along with that it includes your environment config, and then the some LCR item, and then it has this various. So LCR item is a sequence item, we'll look at it. So we have a bunch of like TX and RX scoreboards, we have modem scoreboard, then the interrupt coverage monitor, we have TX coverage monitor, RX coverage monitor, modem coverage monitor, then the rate checker, baud rate checker, and then the reg access coverage monitor. Okay, then the environment itself. So this way we have all the files that are we are going to use as a part of this environment package are listed over here. Of course we are going to be looking at one flavor of each. So one flavor of scoreboard, one flavor of agent, and then one flavor of coverage monitor, so on and so forth, right? So one flavor of each unique component. We will be doing the code deep dive as we go further. I would like to keep repeating this point because it's again another important point, that when we think of UVM Testbench, as we are about to now jump into the details of UVM Testbench, I don't want you guys to be thinking, oh, I don't know anything about UVM Testbench, how am I going to learn it, right? So that thought is going to come again and again, although you are introduced to the core concepts in detail, but still that thought will come. What I want you to think about it is, you think about what are the steps that are involved in building test bench. Stick on to that, because those are the things that you know. Okay, and you have to always go from known to unknown. Okay, so those are the steps you know, you have to hold on to that. Using that as a reference, you have to look at UVM, because fundamentally we are doing nothing new, right? Fundamentally, we are following the verification process that we have already described, and in that verification process, part of test bench architectures were layered, and then few steps that we have to do. Like for example, how do I connect test bench to DUT? That I need to know that, right? And how do I configure the test bench to test intent? How do I do that in UVM? Then how to generate stimulus to meet the test intent? How do I generate stimulus in UVM, right? And then how do I do self-checking in UVM? And then how do I do functional coverage? If you understand these 5 components, it doesn't matter. Got it, right? So it doesn't matter in the sense, what I'm trying to say is you understand what needs to happen in order to do each of these components, correct? And now all that you are going to really learn is how to do it. So it's not that you are learning something which you totally don't understand. You already know that these are the steps and how these steps could be done or how do they look like. You have some sense of it, right? So what you are going to do is you want to translate that sense as to how same thing is done in the UVM. Okay, so look at it from that point of view, and your overall understanding will become much better. Let's start off with the first step. How do we connect our DUT to test bench? So this is the first step. What are we doing? So we are looking at a tb-top file, and the snippet that I have put over here, you can find it in the tb folder in UART example. Okay, you will be able to find this file, and I have already taught you how to use some of the find commands. So you can always grep for, let's say, xargs grep for UART 16550, and you will be able to see where this particular file is present. So that's how you have to start exploring the code. Okay, so in the tb-top, what we are doing first thing is we are instancing our DUT. Okay, and then our DUT from our interface understanding about the UART DUT that we have built, we know that it's going to contain APB interface, it's going to contain an interrupt pin, it is going to contain the serial transmission and reception pins, and a bunch of these modem interface pins, and then there is one baud rate output. So this is the this output is not a part of functional specification. Currently it's done to ease the implementation of checker, but this the top whatever the 4 boxes that are present, they are the ones that are part of this 16550 specification. So what do we do? So at the test bench top, we instance each of the interfaces, nothing new, right? So we have done this instancing of interfaces even when we did the FIFO test bench. So we instance each of the interfaces. If the interfaces had any input ports, we pass those signals, clock and reset. I'm not showing the generation of those 2 signals, but you know how to generate clock and how to generate the resets, right? So first you instance all your interfaces, then those interfaces you connect it. Step 2 is you connect those interfaces to your DUT ports, right? So you install the interface instance name dot whatever the signal that is present in the interface corresponding to this particular DUT port. So for example, if I look at how the APB interface is defined, I have these 2 inputs with a logic type which is sort of equivalent to a wire without multiple driver. I have declared all my interface signals, and those interface signals I am connecting it over here. That's all I'm doing. So each of these interfaces similarly will have different logic type of wires, and all that I'm doing is taking them, instancing them at the tb-top. Once instancing, this instance dot whatever the corresponding signals, I'm connecting it to the DUT ports using the dot signal name type of a notation. I'm using the signal name and connecting, and not by the position. And once I have connected it, what I am doing is I am taking this interface. Now this interface I now need to hierarchically pass it down to the test bench. That is the main part. So this 2 steps that I talked about, declaring a SystemVerilog interface, instancing the SystemVerilog interface, then connecting it to the DUT ports, is same, is no different compared to UVM, right? It is all SystemVerilog code. Again, I would like to emphasize, UVM is nothing but a SystemVerilog code. Don't think anything else. Okay, so we have done that. Now question is, how does UVM ease passing of this interface to different components in the test bench? So that is done with the help of the config database. So what you say is, we don't need to instance the config db. So config db is by default available. So you say config db hash This is the parameterization. So it always config.db is parameterized with the data type that you are putting it in or data type that you are trying to extract. So here we are parameterizing it with the virtual APB interface. Okay, so this APB interface, whatever we have defined, this is a static interface. We are passing the virtual type because Testbench always deals with the virtual type. So we are passing virtual APB interface, and so you imagine like this, right? So this UVM config.db is parameterized with the type, the data type that it is trying to store. So with APB interface it is parameterized, and then within that parameterized class what we are doing is we are saying set. Okay, so set takes 4 arguments. It takes in the hierarchy, it takes in after hierarchy what is the leaf of that particular hierarchy, and then the name. This is the key value pair that we were talking about, the name with which we want to store, right? This is the key. You can think of it as an associative array. And then the value here is nothing but the APB itself, right? So the name of our interface instance is capital APB, and that is what we are passing over here, and this is also capital APB. This is just a string. Okay, so with this string it stores the APB. So anywhere, now what we are saying is that it has been, so at the top of the test bench there is no hierarchy for the test bench. Okay, so what we are saying, there is no like environment.agent. nothing is available. So it's only UVM desktop. UVM desktop will always remain UVM desktop. UVM desktop is the object that gets created within the UVM. So you have to use, whenever you are setting any interface into config.db at your test bench top, you have to always use UVM desktop. That is the way UVM recommends you to do it. So there is no additional hierarchy, so we pass null, and then the desktop is the final hierarchy at the top level. Okay, with that we are passing the APB. APB is the name, and with the same name as interface we are using for the ease, and we're passing that particular interface. So same thing is done with all of them, right? So all of them meaning we are passing RX UART that we had connected over here, right? And we are passing TX UART that we had connected over here, and then we are passing the modem interface. If you see here, modem underscore IF capital modem, which we had connected it over here, we are passing it over here, right? And then we are passing the IRQ interface which we have connected over here. So each of those interface with same name can be different, but just to make it easy to understand, we are using the same name. You pass the same name and set it that think of this as like sort of a whom it is supposed to reach, right? That is what we are saying here, the to address, right? So we are saying it should reach UVM desktop, and we are saying it should reach UVM desktop because by default when the UVM root starts, it will have only desktop, and the desktop will be created with the name of the test that you are trying to run. Okay, so any test that is running is called as desktop in the UVM overall hierarchy. Okay, so we are saying whoever is running with whatever, once you pass a test name, that test will be running. Whoever is that is always inferred as UVM desktop. So we want to reach him. Okay, and he is at the top, so there is nobody else. So we are saying it is UVM desktop, and once we say this, we will see. So idea is once you set it, the test that is running can get it. Okay, and it gets it and passes it down the hierarchy. That is the next step that we will be seeing. So we looked at in the previous slide, so that in the initial block through the config.db we set everything and we call the run test, right? So we call the run test in that initial block, and once we call the run test, what happens is it calls the run test within the UVM root, and that UVM root will then start the phasing. So this part we have seen it in the core concepts as well. So it starts the phasing, and in the phasing I have told you we have these 3 main phases. We have build phase, we have run phase, and the cleanup phase. And as a part of this, we are going to be primarily focusing on what happens in the build phase, what happens in the connect phase, right? And then what happens in the run phase, and then what happens in the check phase, and what happens in the report phase. These are the phases that we are interested in, which we are going to be looking at in the next few slides.